All right, so this is section 4.6, and it's still dealing with exponential and logarithmic equations now. And with the equations, this is where we're going to use some of those power properties and the product and quotient things to actually help us solve these types of equations. So actually, we have to first learn this one key one here, and it's called the one-to-one property of exponential functions. And it's kind of nice because what happens is when we do this, it makes our life so much easier. So if we have two things that are the same base raised to whatever power it is, in this case they call it S and T, then what happens is, since they're the same base, we can say then S is equal to T. So we just drop our bases, keep our exponents, and set them equal, and then we can solve the equation or whatever it is from there. And so this is the key for one-to-one properties of exponential functions. And again, they have to be the same base. So looking at our example here, 5 and 5, those are the same base. And so what this says is we can just take our exponents, 2x and 3x plus 2, and set them equal. And so that makes this problem so much easier. Now what we could have done is we can take ln of 5 to the 2x equals ln of 5 to the 3x plus 2, bring our 3x plus 2's down, divide both sides by the ln of 5, and guess what? That goes to 1, and guess what's left over? 2x equals 3x plus 2. And that's all the reason why we can do this thing, because again, if we had taken the ln of 5 to the 2x equals the ln of 5 to the 3x plus 2, we bring those down, and then ln of 5 divided by the ln of 5 is 1, and you just have 2x equals 3x plus 2. So that's why this works. And now we just simplify here. So let's subtract 3x. And so minus x equals 2, or x is equal to a minus 2. Okay. And so that gives us the solution to this equation of exponential function, or exponential powers here. Now the next one, we have a 5 and 25. Those are not the same base. So we can't use this as it sits. But can we rewrite the 25 so it actually is the same base? Well, we can, because that's 5 to the 2x here. Well, 25 is 5 squared, and then that's raised to the 3x plus 2. And so if we simplify that, that's going to be 5 to the 6x plus 4. And so now we have 5 to the 2x equals 5 to the 6x plus 4. So now we have the same base. We can set the two exponents equal. 2x equals 6x plus 4, and solve. So if we subtract 4x, and or 6x, we're going to get 4, I don't know. And so that's going to be a minus 4x equals a 4, so x equals a negative 1. And so that then would be our solution to the original problem that we had to simplify by saying, well, 25 is just 5 squared. And so sometimes you're going to have to convert this. Maybe you had 4's here, and then you had a 64. You'll have to convert it to base. The base is 4 instead. And so all those things will work. And again, it's just a matter of thinking about it. And usually they set it up pretty nicely. So one of them is going to be the factor you need, and then the other one you just have to get to match the same thing like we did here, the 5 and the 5. Sometimes it'll be 4 and 4, 3 and 3. But again, it all works out once you get it converted and you take your powers, multiply them, and then just set your two powers equal to each other. All right, what about this one? Here we have the square root of 5. That doesn't really look like a base 5, but if we rewrite this as 5 to the 1/2, because that's what square root is to the 1/2 power, now same base. And so we just set the exponents equal, and that one we didn't have to do any work. It was just x is equal to 1/2. Okay. What about the next one? Okay, so we have 2x on the left. Now we have to figure out what can we get to there, that negative 100, to get to some base 2. Well, no matter what you take 2 to any power, we're never going to get to 100. And because of that negative there, that's never going to help us either. And so this one has no solution. So if you're working along and you get one where you have a 2 and something you can't get to the same base, or it's negative, things like that, and you never can get it, so it's going to be 2 the same on each side bases, then you're basically just going to have no solution. You can't work that problem out. Okay. So sometimes that happens, but those are more rare ones than if you have things like this where you have to manipulate one side to make it so it looks the same as the other side as far as the base goes. All right, so if we need to solve exponential equations using logarithms when common base can't be determined, that's going to be pretty easy. What we're going to do is we're going to take logs of both sides. And again, depending on what you have, if you have things with has powers of 10, then we might use the common log, which is base 10. And if none of them have a term of base 10, then we're just going to use natural log. Again, most of the time, I'm going to just switch it to natural log because it works. It doesn't matter. And it's going to be just easier for me to write ln than log. So I'm kind of lazy when it comes to that. And then after that, we're just going to use our rules of logarithms to solve for the unknown. Okay, and so this is kind of when we start using our power rule, our product rule, and our quotient rule to actually solve these. So here we have a base 2, here we have a base 3. Those aren't the same. There's no way we can get them to be the same. And so what I'm going to do is I'm going to take the ln of both sides. All right. So what do? Well, now we can use our power rule. And we can bring this down in front, and we can bring that whole x plus 1 down in front here. Okay, so what does that give us? Well, it gives us x ln of 2 equals, then we have x plus 1, and then we have ln of 3. Okay, so now what can we do? Well, now it's kind of one of those things. It depends on how you want to kind of look at it. But what we can do is we can take this ln of 3 and distribute throughout here. Okay, and so we get x ln of 2 equals, now we have x ln of 3, and then 1 times that is just plus ln of 3. So all we did is distribute over here to get rid of this binomial here, and so we have something that looks like this. Now we want to get all the variable terms on one side, so I'm going to take them to the left. So that's going to subtract x ln of 3, and I'm going to subtract x ln of 3. So now if I move up here, I have x ln of 2 minus x ln of 3 equals, and then on the right, I just have ln of 3. Now I have x in both of these terms, so I can factor that common term out, and I have ln of 2 minus ln of 3, and that equals ln of 3. Okay. Now what I can do is I can divide that by ln of 2 minus ln of 3, and divide that by ln of 2 minus ln of 3. And so that gives me just x equals this whole term here. Now, what can we do? Well, if they actually want us to solve to some decimal place, we can just plug that into our calculator and get a value. And so if we did that, we have, let's see what we get. Where'd my calculator go? So if we clear that, we would have ln of 3 divided by, and then we have parenthesis, ln of 2 minus the ln of 3, parenthesis again. So we get negative 2.7095. So we had over here negative 2.7095 if they say wanted it to 4 decimal places. Okay, so that would be that. But we could do something else too. We could simplify this whole piece here and make it a little nicer. We could say, well, that's equal to, on a numerator, we'd have ln of 3. Now, when we have that, we can make that and say, well, ln of that minus ln of that is going to be the ln of that. That's going to be in the numerator. The denominator is going to be this. So we'll have ln of 2 over 3. And I think at that point, I wouldn't try to convert it anymore. I would say maybe that would be as far as I'd want to go and simplification. This one would be fine as well. And again, if they wanted a number, I could have that. So, we could keep going longer and longer and doing more and more, but that's going to start getting really ugly looking if we do that one. We're going to have weird things. And so I would say keep it at that, because we could go from here back into our original problem without simplifying anymore. If they wanted the number, then we could just have our number. So that's kind of what I would do as far as that one, and as far as I would go as well. Now, what about the next one? Well, the next one looks really easy, so let's do that. So different bases again. Basically, I'm going to do the same thing. I'm just going to take the ln of both sides. So that's ln of 2 to the x equals the ln of 3 to the x. Now I'm going to bring the x's down front, so I have x ln of 2 equals x ln, let's do that a different way here. Ln of 3. Now I need the x's all on one side, so I'm going to subtract off and bring it over here. And so that says x ln of 2 minus x ln of 3 equals 0. Because when you subtract it off here, you're going to get 0. Now I have that common do just like I did here, and I factor it out. I have ln of 2 and then minus ln of 3 equals 0. Now I want to divide that, so if I divide both sides by that whole thing, I have ln of 2 minus ln of 3, and if I divide that by ln of 2 minus ln of 3, well, what does 0 divided by anything give you? Well, that's 0. So that's what my x is equal to, is just 0. And if you think about that, the only way both of those are going to equal is if we take 2 to the 0, which is 1, is equal to 3 to the 0, which is also 1. So that makes sense as far as our answer goes, because that's the only values that will work in here. If we plug anything else in here, we're going to get factors of 2, and here we're going to get factors of 3, and those won't actually equal in that case. But that's how you get to it. You have to do the whole, changing it to logs, simplifying the logs, getting the things together, factoring out, and then dividing at the end to show that x is equal to the 0. All right, now if we have equations containing the e value, and that's the exponent, e to the 1 is our values we're looking at here, we're going to have to use natural log. So this time we can't use just plain log. We have to use natural log, because when we do this, when you take the natural log of something, especially when you have like ln of e to some x power, we know that we can bring that down, and then ln of e is just 1. And so then we just have whatever the exponent is. And so that's going to help us solve equations. So that kind of goes back a couple sections, but it also goes back to the power rule, and we can bring down that value here. All right, so what we're going to do is we need to isolate our exponent first. And so to isolate the exponent first, that means we just want this piece on one side, and then everything else to the other side. Well, how do we do that? Well, we do 3. And so that gives us e to the 0.5t equals 11 over 3. And I'm just going to leave it as the fraction 11 over 3. All right, now we know if we take the natural log of this side, we can bring down that exponent and basically simplify. So I'm going to take the ln of that side, and I'm going to take the ln of that side. Again, using the power rule, that gives me 0.5t ln of e, and that equals ln of the 11 over 3. Now, ln of e is just 1, so now I have 0.5t is equal to that. Well, what is 0.5? Well, that's 1/2 t is equal to the ln of 11 over 3. So how do I get rid of that? Well, I multiply both sides by 2. And so on the left, I get t. Now I have 2 times ln of 11 over 3. Well, remember, we don't really want to have these numbers out front. We want it to put it back into here, so we want to kind of condense it. And so then that says t is equal to ln 11 over 3 squared. Okay. Now, if we wanted to, we could square each of those, but I think leaving it at this point here is going to be good enough as far as solving for the t, because then if you needed to, and they asked for what is the value, you could actually take that and solve for it and plug it in your calculator. But they don't ask for this. They just want us to isolate e and then solve for the actual value in terms of the logarithm. All right, well, what about this one? Well, look at this. We have 3 plus e to the 2t equals 7e to the 2t. Well, that and that are the same. So if I subtract e to the 2t, that gives me 3 equals 6e to the 2t, because this one has a 7, this one has a 1. 7 minus 1 is going to be the 6. So what we're going to do now is we're going to simplify. So we're going to divide by 6. So that gives me 1/2 equals e to the 2t. Okay. Well, now I'm going to take ln of both sides. And so now I have ln of 1/2 equals the ln of e to the 2t. Now I'm wanting to solve for the t, so that means I use my power rule to bring that down. So that gives me ln of 1/2 equals 2t ln of e, which we know is 1. Okay. So now we have this. So what does that tell us? Well, now I can take and multiply both sides by 1/2 to get rid of that 2. And so I have then t is equal to 1/2 of ln, well, let's kind of, ln of 1 over 2. Okay. Now 1/2, if we take that up to the top, that's going to give me ln, and 1 to the 1/2 is going to still give me 1. 2 to the 1/2 is going to give me the square root of 2. And so I think at that point I would leave this in this form here. It doesn't say rationalize the denominator. It doesn't say anything. It doesn't say to make it to the numerator. And so I would just leave it ln of 1 over the radical 2, and I would be done with that problem. So that's how I'd solve this one. And again, the key was noticing that the e to the 2t is the same on both sides, and it's just going to be the 7 minus the 1 once we bring that to that side. And then we can take the ln of both sides after we divide by the 6. Okay. All right, so this one is going to be a little more complicated because we haven't thought about factoring powers like with e or anything else, but this is what we're going to have to do. So sometimes we're going to get extraneous solutions, which means they don't satisfy the original equation algebraically. So how are we going to do this? Well, remember, logs always have to be positive. So looking at this, I wouldn't see what I would have to do, but what we have to do is we have to get everything on one side, then factor it, and then set each of those factors equal to 0 and solve. So what I'm going to do is I'm going to subtract e to the x, subtract 2, and so that gives me e to the 2x minus e to the x minus 2 equals 0. Okay. Now what we can think of this as is x squared minus x minus 2 equals 0. And can we factor this? Well, that's going to be x and plus and minus, and we want the larger one to be negative, so the larger one's 2 and 1, and so it's going to look something like that when we factor it. But what is x now? Well, x is e to the x, and so what we're going to have is e to the x plus 1 and e to the x minus 2 is equal to 0. So that's how this is going to get factored, based on looking at it as just the x's only instead of e to the 2x and e to the x and the minus 2. So what we have to do is kind of have to look at it in a different format so we can recognize that's the form it is, because here we have 2 of them, here we have 1, and here we have 0. Okay, and so that's the form we have. And so now we set each of these equal to 0. E to the x plus 1 equals 0. And we have e to the x minus 2 equals 0. Well, here, e to the x equals negative 1. here e to the x equals 2. Now to solve this, we're going to have to take the log of both sides, so that ln of e to the x equals ln negative 1. Right there, we fail already because we can't take the log of a negative. So this doesn't work. Okay, so that's going to be a bad solution no matter what we do because we can't take the log of a negative. Now this side though, ln of e to the x equals ln of 2. Well, now x comes down here. ln of e is 1, so we have x equals ln of 2. And that then is our solution to our original equation. Okay, and that's the only one that's going to work. Because the other one, what happened is we're going to get some ln of a negative. It's undefined. We can't do it. And so that is an extraneous solution that just, it doesn't work. Okay. So that's our final answer there, x equals ln of 2. And if we needed to, we could always plug it back in and verify that that would be the correct answer. All right, so here we're going to use the definition of a logarithm to solve logarithmic equations again. And so it says for any algebraic expression S and a real number b and c, where b is greater than 0 and b cannot equal 1, if we have this log base b of s is equal to c, if and only if, and now we're just going to take b to the c is equal to s. So just basic log functions that we learned a long time ago, we're just going to take the base raised to the whatever the y is equal to this, which we used to call x, okay? And so that's what we're going to do in this case here. And what we need to do is, I need to get the log by itself. Well, how do I do that? Well, if I subtract 6 from both sides, I get the ln of x equals, and that's going to be 4. Now, what do I know about ln? Well, if I need to have it in a form like that, that's going to be log base e of x equals 4. Well, here I just say, well, e to the 4 equals x, just based on our little formula, b to the c equals s. And so when I do that, that's going to be my solution. Now, it doesn't actually say find out what e to the 4 is to what decimal place. So what it probably wants is some exact answer, and that would be the most exact answer, just e to the 4. Okay, now if they said solve and round to the 4 decimal places, we could plug that in our calculator and get it to the 4 decimal places. But when it just says solve, they want the exact value, which in this case is e to the 4. Okay, so the key again is get it into form where we have the log on one side, everything else to the other side, and then we can use our definition b to the c is equal to s. All right, so let's do a couple more here. So on this one, what are we going to do? Well, I'm going to go ahead and say, I could divide by 5. I could do a lot of different things. Maybe I'll divide by 2 to get the 5. So ln of x plus 1 equals 5. Now here I'll have e to the 5, because remember, that's log base e. So e to the 5 equals x plus 1. Now if I solve for x, I subtract 1 on each side, and I get x equals e to the 5th minus 1. And again, we want exact values because it doesn't say it around to the nearest 4 decimals or whatever. And so we just get e to the 5th minus 1. All right, we can also use our calculator to solve equations. And so instead of using logs, we can plug it into our calculator. And so if I remember that, I can go over here. And what we're going to do is, let's clear our graph here. So we'll clear that and clear that. We're going to type in the first equation on the left side, 2 to the x, and that was here, 2 to the x, equals the other side, 1,000. Okay, and so then we can graph that. And again, we're not going to see the top graph because I'm not going to make it go up to 1,000. I'm just going to say, okay, well, let's find where they intersect. So that's second trace. Intersect is 5. First curve is blue. Second curve is red. I guess, I don't know what it is, so I'm going to enter, and it tells me my answer. So it intersects at 9.9657 and 1,000. And so that is the answer to what x is. So x is the 9.96, whatever it was, 966. And so if we round to 2 decimal places, I forgot it had 2 decimals, 9.97. And again, that's something easy. And we've looked at that before where we set one side equation equal to the other side. We plug that into y1, that one into y2, and then we find the intersection with our calculator second trace function, and it tells us what the value is. And we're looking for the x value, okay? Because the 1000 over here is our y, and this is the other equation. So we know y is equal to, and we're solving for the x. All right, what about this one? And I have two left, I guess, as far as questions go. So I'll finish up even if you have to leave, Madeline. So here, what I'm going to do is I'm going to basically simplify here. And if I do this, I'm going to what I'm going to do is I'm going to say, well, my x is over here. I have logs, but I'm going to say this is log base e is equal to this, because ln(1) is just a number. So I can consider that a number and forget about it being ln for now. And so I can say e to the ln of 1 is equal to x squared. Now e to the ln of 1, if I plug that in my calculator, that tells me 1 is equal to x squared, okay? Now, if I want to solve this, I have to solve the equation. So I have to subtract 1 on both sides. So that gives me x squared minus 1 equals 0. So if I factor that, that's going to be x plus 1, x minus 1. And so when I simplify those, set each of them equal to 0, I get x equals minus 1 and x equals plus 1. So I get two solutions, and then if we plug them both in, you know, they both work, because if you think about 1 squared is 1, that matches. -1, the whole thing squared is 1. It works on both of them. And so I have both solutions being true here. Now, the last question I have is with radioactive decaying. And so they give us a table of all kinds of elements that are radioactive, what their use is for, and then their half-life. And then we have the equation A of t equals A sub naught, which is the amount initially present, times 1/2 raised to the power t, which is the time period which is substance is studied, divided by capital T, which is the half-life, which they give us in the table here. And so what we want to do is, in this case, how long will it take before 20% of 1,000 gram sample of uranium-235 has decayed? Okay, well, what is 20% of 1,000 grams? Well, that's going to be 200. And so how much is left over? Well, that's 800. So that means this is going to be 800 grams. Okay, yeah, grams. And our zero time is going to be 1,000. So we've decayed 20%, which is 200. And so what we need to do then is simplify. So 800 is 1,000. And then we have times 1/2 raised to the power t, which we don't know, that's what we're searching for, over the half-life, which is this huge number here. And so that's 703,800,000. All right. Well, we know that that's some, you know, thing to the power. And so that's, we can use exponents here, that functions, log functions. And so whatever we do, we have to get this by itself. So we have to get rid of this 1,000. So I'm going to divide by 1,000. Well, if I divide by 1,000, that's just 0.8. So that's equal to 1/2 to the t over 703,800,000. All right. Now, at this point, I'm thinking, okay, well, nothing's base 10, but if I take the log of both sides, I can bring down my exponent here. I can take the log of 1/2, no problem. I can take the log of 0.8, no problem. And so that's what I'm going to do. I'm going to take the ln of this and the ln of this. So now I have ln of 0.8 equals, now I'm going to leave some space because now I'm bringing everything down in front here. So that's going to be t over 703,800,000. All right, now it's set up nicely. I can solve for t. Basically, I have to divide both sides by ln of 1/2. And to get rid of the fraction here, I'm going to have to multiply both sides by 703,800,000. So I'm going to multiply this side by the same thing. And so then I just have to plug that whole thing on the left into my calculator, and I'll get t is equal to, and now if I plug that in, I had the 703, and then it was 800,000, and then it was times, and then we had the ln of 0.8 in the numerator divided by the ln of 0.5 in the denominator. And so I get that many years. And so if we go back over here, how long will it be? It's going to take 3.2 years. So it's going to be one long time before 20% of that 1,000-gram sample is decayed. So that's why everybody's worried about all the nuclear waste, because that's a long time before even just 20% of it's decayed. Think about if we wanted all 100% decayed, that's going to be very, very long time, because our half-life is that long. So it takes that long for half of it to disappear, and then it just continues on and on and on. So that then concludes 4.6 as well. So then we only have, I think, 4.7, and do we have, what else do we have? Is it 4.8 also? Just 4.7. So we only have one more section. So actually we could have probably Wednesday and Thursday of review if you wanted that.
That sounds perfect.
All right. So I will see you next time.